The film that you are about to see was made to show to engineering students who are just beginning their study of the mechanics of fluids as an engineering science. Such a course, to be effective, must include a series of well-planned laboratory experiments. This would be a difficult task for even the largest institutions, if only because of the variety of phenomena that are involved and the complexity of the equipment that would be necessary to demonstrate them on demand. The smaller institutions are even more handicapped in this regard. When it comes to the selection of natural phenomena as examples, the use of films is the only solution for colleges, both large and small. This film and those that are to follow are therefore intended to provide illustrative material that will effectively supplement what is normally given in a good college course. The ancient Greeks' classification of matter into the elements earth, water, air, and ether was surprisingly prophetic of the present-day classification into solid, liquid, gas, and plasma, the latter denoting the electrically charged particles encountered in outer space. If one includes the plastic flow of the solid state, all four classes are seen to have certain fluid properties. Usually, however, only liquids and gases are included in the fluids category. With this restriction, the part that fluid motion plays in one's everyday life is astoundingly broad. Almost every aspect of our work, relaxation, body care, and nourishment involves fluid flow in one way or another. Many of these actions have become so commonplace that we no longer give them even passing thought. Nevertheless, anyone who fully understood the mechanics of each elementary phenomenon that is reproduced in these familiar scenes could truthfully claim to know more about the subject than anybody on earth. Cigarette smoke is a necessity only to some, but the water that we drink and the air that we breathe are vital to life itself. Hence they are subjects of widespread study, as is the very blood that flows in our veins. Equally important to our existence is the fluid flow involved in the hydrologic cycle of evaporation, precipitation, infiltration, and surface runoff. We take the weather as a matter of course. When it rains, most of us simply let it rain, as it has been doing for billions of years. Some of us, on the other hand, are engaged in its prediction or its recording. For such runoff as this not only provides us with water, transportation, and power, but during these billions of years has helped give the surface of the earth the form that it has. Geologists study the flow of water, sand, and snow that they may better understand the work that has been done in ages past by rivers, winds, and waves. Meteorologists and oceanographers, of course, are interested in present-day winds and waves, in the Gulf Stream and other currents that exist in the ocean, and in similar prevailing air streams in the skies. Thanks to aquatic sports, our attention has been drawn to the fact that there is almost more life below the ocean surface than above. The secret of the unbelievably low resistance that many of these natural underwater bodies possess, especially porpoises and dolphins, would be invaluable to designers of ships and planes. At the very least, the dolphin has contributed the principle of this efficient racing kick. This barefooted water skier, on the other hand, has borrowed the principle of free surface planing used in these rather more stable, high-speed boats. Men like Leonardo da Vinci watched birds in flight for many years with only sketches of imaginative flying contraptions to show for it. But in the present century, man has progressed with ever-increasing rapidity from toy gliders to spin-proof family planes, from formation flights like these are the Navy's famed Blue Angels, to intercontinental missiles like the four-stage Scout of the National Aeronautics and Space Administration. With the satellites, aeronautics has now become astronautics, the glamour profession of engineering science. There remain, however, countless other professions dealing with fluid motion, and upon these, as much as upon outer space, our civilization will long continue to depend. River barges must be built, fruit trees must be sprayed, oil, upon which our highly mechanized existence depends, must be sought, pumped, refined, and distributed, as in this small section of the vast complex that is the humble oil company. A great variety of chemicals must be manufactured. All sorts of paper must be made, as in this consolidated mill for fine magazine stock, now seen in slow motion. Drinking water must be purified and sewage made harmless before being returned to our streams. And the many metals that our industry and construction require must be smelted, as in this open hearth of United States Steel. In order to describe such a variety of flow occurrences, to design vehicles and conduits and machines which in themselves produce fluid motion, and then to predict their efficiency of operation, we must first agree upon a special physical terminology. Fortunately, the same terminology is used in the various phases of mechanics, whether solid or fluid. While a great many different terms are used in this one engineering science, terms like intensity of shear, or momentum, or rate of doing work, and while different units of measure could be devised for each one, actually the number of terms and of units is reducible to only three: length, time, and either mass or force, with the possible addition of temperature, if one wished to include certain thermodynamic phenomena involved in high-speed flow. Any type of fluid motion is thus describable quantitatively in terms of units related to these three or four dimensional categories. The shape of a fluid stream can be described in terms of length alone, whether one measures the diameter of a jet with a micrometer or the depth of a river with a staff. The principle is the same. The area of the flow passage is then determined by planimeter in terms of length squared, and the volume is length cubed. The same procedure is used to define the form of a ship hull, whether a prototype or a model such as this. Scale is a very important factor in fluid mechanics, for the size of a boundary is as important as its shape. This microscopic cell, for example, is less than 1/1,000,000th as large as this flexible British oil barge of similar form. Time, the second fundamental dimension, was once measured appropriately by water clocks such as this replica of an Egyptian clepsydra, which marked fractions of a day 3,000 years ago. But we know it most intimately as it is indicated by a watch in hours, minutes, or seconds. Some flow occurrences take place so rapidly that electronic means of splitting seconds into 1,000 or even 1,000,000 parts must be employed. On the other hand, such natural phenomena as floods or hurricanes require days to advance across the Earth, and cycles of solar activity are reckoned at Mount Palomar in years. The combination of length and time serves to define such terms as speed and rate of flow. Speed, which signifies distance traversed per unit time, is measured by propellers, anemometers, and current meters such as these. Velocity is a combination of speed and direction, each of which is seen from a pattern of particles carried by the flow. Acceleration, or velocity change per unit time, is also represented by the changing flow pattern. Both length and time scales are involved in comparing small and large patterns. This vortex in a small tank is basically similar to the vast cloud formations of very small rotational speed observed from a Weather Bureau satellite. Both have much in common with the tremendous spiral nebulae in remote parts of space as photographed at Palomar. Force and mass, one or the other of which is the third fundamental dimension, are related through the Newtonian equation. However, they are often confused, largely because a particular type of force, the weight of a body, or the attraction of gravity upon it, is here on Earth an almost constant multiple of its mass. One could measure mass with a centrifuge through use of the Newtonian equation, accelerations thousands of times that of gravity being obtainable. Usually, however, we measure mass indirectly on a beam balance by comparing the weight of the body in question with that of a standard body, both under the same gravitational conditions. But a spring balance measures absolute force and would hence indicate a zero weight for a body out in space or immersed in a liquid of equal density. Mass acceleration, however, photographed in slow motion, requires force even when the mass is weightless. Mass density and specific weight are determined by measuring the mass or weight of a known quantity of a substance, contained, for example, in a calibrated pycnometric flask. Fluid pressure has the dimension of force per unit area. We are familiar with barometric pressure, the force exerted by a column of the atmosphere on a unit area of the Earth's surface, and its relation to the highs and lows of a weather map. Blood pressure, as an indication of physical well-being, is also a common concept of our everyday life, as is the hydrostatic multiplication of force in various forms of the hydraulic press and hydraulic lift. Pressures below atmospheric, the principle of any siphon, are measures of a partial vacuum. The ancient Greeks said that nature abhors a vacuum. But even with commercial machinery, man is able to remove a surprisingly large percentage of the air from containers. With mercury vacuum pumps, he is approaching the complete void of outer space. The tangential force known as shear, which resists fluid deformation, is due to the property called viscosity. We are aware of this property primarily in connection with automobile lubricants, different grades being purchased for cold and warm seasons. Liquids can become extremely viscous, like cold honey, here compared with water, which is viscous to a far lesser degree. As seen from this sheet of glass falling on another sheet without breaking, the cushion of air between them is also viscous. Air is actually 15 times as viscous as water, and hence 15 times as stable against the onset of turbulence. But once turbulence begins, whether in a plume of rising smoke or a plume of falling silt, viscous shear occurs in every eddy, large and small, and the effort required to maintain the flow increases greatly. Another fluid property of importance is elasticity, the ratio of applied pressure to the relative change in density that it produces. Though usually considered incompressible, liquids are sufficiently elastic to permit submarine signaling and sounding by the generation and reflection of elastic waves, as in this Corps of Engineers Mississippi River measurement of channel topography. When a valve is suddenly closed, elastic waves also cause the noisy plumbing phenomenon known as water hammer. The compressibility or elasticity of gases is represented by the equation of state of thermodynamics, in which P, rho, and theta are the pressure, density, and temperature already discussed. V bar is alternatively the volume per unit mass, and m is the molecular weight of the gas. The changes that you see going on as this cylinder of air is compressed and then allowed to expand are in accordance with this law. Note the temperature creep due to heat conduction. Our object in studying fluid motion is to gain an understanding of the mechanical principles that are involved, so that this knowledge can be applied to engineering design and control of natural and man-made phenomena. The details of these principles will be illustrated in subsequent films. In your classes, you will learn to apply them singly and, where possible, in combination. For the present, let us give our attention to the very many problems that are so complex that their analytical solution is still impossible. It is in their empirical solution that the scale model has proved its worth. Throughout the country, there are laboratories, largely supported by the federal government, which have as their primary purpose the small-scale simulation of prototype phenomena prior to final design and construction of the actual structures. Model similitude, of course, is also based upon physical principles, simple as these may be. One principle states that if a case of flow depends upon only 4 variables, the geometric scale, the velocity of flow, the force exerted by the fluid on the boundary, and the density of the fluid, that these 4 variables can then be combined to form a single non-dimensional parameter. And that, in addition, this non-dimensional ratio must be a constant. This non-dimensional parameter is frequently called the Euler, or Euler number, and given the symbol bold-faced E. This principle then states that 2 geometrically similar states of motion, depending upon only these 4 variables, must of necessity also be dynamically similar, because the Euler numbers are the same. Almost any unstreamlined device moving completely submerged is one for which the Euler number is essentially constant. A parachute is a perfect example. In fact, the motion of this very large naval one in air is so well simulated at reduced scale in a water tunnel of the Navy's David Taylor Model Basin at Carderock, the model opening time and drag are directly convertible to field conditions. If gravity is also involved, an additional ratio, called the Froude number, would exist. The Euler numbers, which would then depend on the Froude numbers, could be the same only if they too were the same. Evidently, if 2 geometrically similar flows were to be dynamically similar, the velocities would have to vary directly with the square root of the lengths. Though overflow structures like Grand Coulee Dam of the Bureau of Reclamation are dynamically similar if geometrically similar, jet effects, such as those at the Bureau's Friant Dam, or in this model flip bucket at its Denver laboratory, definitely do depend upon the Froude number. The same is true of wave forces on breakwaters, photographed here by the Corps of Engineers in Hawaii, and here modeled in the Corps' Waterways Experiment Station at Vicksburg. One complexity that obviously cannot be modeled is the formation of spray. If, instead of gravity, the viscosity were involved, ratios known as Reynolds numbers would control the Euler numbers, and the velocity should then vary inversely with the length. The Reynolds number becomes the criterion of similarity in the motion of submerged streamlined bodies, like submarines and airplanes. This model plane is being assembled in a Langley Field shop of the National Aeronautics and Space Administration for observation in a spin tunnel. And here a vertical takeoff model is being tested by the NASA in a regular wind tunnel. The results in either case are directly convertible to prototype scale through constancy of the Reynolds and Euler numbers. Ships that move on the water's surface involve both wave resistance and viscous resistance to their motion, and hence for similarity require that both the fluid and the Reynolds numbers remain the same. This is physically impossible at reduced scale if the same fluid is used, as will be true of this model now under construction, and hence the fluid criterion is followed and the Reynolds number effect introduced later by computation. These successive steps in the preparation of a small-scale model at the David Taylor Model Basin culminate in its suspension from the carriage of the towing tank for tests under severe wave conditions, as photographed in slow motion. Obviously, modeling a phenomenon so complex as the submarine launching of a Navy Polaris could be accomplished only by breaking the phenomenon up into a number of parts to be simulated separately. This air view of the confluence of the Arkansas and Mississippi rivers illustrates another class of flow problems involving both gravitational and viscous aspects. If such rivers were reproduced at a scale small enough to include all parts of interest, as in the Waterways Experiment Station's Clinton model of the Mississippi system, the depth would be a small fraction of an inch. Instead, the model is built with exaggerated depth, roughened artificially until it will reproduce past records, then assumed to be capable of indicating the future. If it is the fluid elasticity that is important, the essential ratio takes the form of a Mach number, the denominator of which, it should be noted, is the speed of sound. The Mach number now controls both the Euler number and the condition of similarity. Flow in which the elasticity or compressibility is a factor is well represented by today's supersonic planes, such as this NASA experimental craft. In the supersonic wind tunnel of the NASA at Langley Field, the sound waves which these planes produce and which retard their flight as water waves retard a ship are observed by the Schlieren process as the Mach number rises. You have just seen 100 different scenes of fluid motion taken from various phases of civilized life. As many more could have been based upon such equally important fields as ballistics, combustion, groundwater, heating and ventilating, hydroelectric power, lubrication, placer mining, smoke abatement, and so on and on. Today, moreover, the horizons of engineering science are advancing at least as rapidly as civilization itself. It's therefore the task of every student engineer not only to learn to apply the principles that are already known, but to prepare himself to assimilate those that will still be discovered in the course of his professional career. The mechanics of fluids is as characteristic of present-day trends as an engineering science could possibly be.